Hello, ladies and gentlemen. Welcome to Buoyancy and the Archimedes Principle. If you have not yet watched the Archimedes principle story or how Archimedes came about with discovering this principle, please go ahead and watch the previous video so that you know the background history. All right, so the story goes, Archimedes discovered this principle while trying to prove that something was made out of pure gold or not. The buoyant force of an object immersed in a fluid is equal to the weight of the fluid displaced by that object. And that mathematical equation describes it very well. Now, let's do a recap. In order to do these kinds of problems, there are several things that you must do. First of all, you must know that forces are vectors. That means they are a scalar quantity or a numerical quantity that have a direction. The force of gravity, or the weight, always points downwards, and you'll see it written as f of g or w, depending on which textbook or which example that you're looking at. Vectors can be added together, but with that being said, you can only add x vectors or horizontal vectors to horizontal forces or other horizontal vectors, and you can only add vertical vectors to other vertical vectors. And for the sake of all of our examples, we will say anything that is going up is positive and anything that is going down is negative. Always, always, always draw a free body diagram or a FBD when you are dealing with these problems. It really helps seeing a visual aid, and it also helps to keep track of all of the forces. Because forces can be a little bit difficult if you can't actually visually see what is happening. If an object is floating, whether it's floating while it's underwater or if it's floating in the air, the acceleration is equal to 0 because all of the forces acting on that object is equal to 0. For example, if we take a look at the little illustration right there on the screen, we can see that there are two forces, and I'm going to let you know, and we can assume that that object is floating. Because that object is floating, the F of B, the upward force, cancels out the WB, or the force pointing downwards. So up plus down, or positive minus this downward, is equal to 0. And please, you must create a net force equation when dealing with forces. These are all just great habits and tools for you to use in order to be able to solve these problems. All right, let's take a look at the definition of buoyancy. Or why buoyancy happens. So objects can float in liquids because of the buoyant force. So the liquids all push up from the bottom of the liquid, and we know that it pushes up more from the bottom because of the pressure equation. The greater the change in height, the greater the pressure. So in a simple term, according to this illustration, the further down you are, the more pressure there is pushing up. Okay? So that results in a greater force. So let's take a look at a couple of mathematical examples. So with all of that previous knowledge, let's jam it all in. We have a box that has a weight of 10 newtons, but once it's submerged in water, it feels as if the box weighs 2 newtons. Now we can substitute the word box for a scuba diver or a swimmer or a fish, whatever the case is. But what I want you to do is to determine the buoyant force. So with all of the tips that I gave you earlier, let's follow all of them and try to solve this problem. I already created a sketch, so if you haven't already done so, please sketch this example and write down the question. After you've done that, we need to label all of the forces. So we have a downward force, and that is 10 newtons. That is also known as the weight, or the force of gravity. We also have an upward force, okay, and we don't know what that is, because that's what the question is asking for. What is the buoyant force? And for these examples, we can assume that the buoyant force pushes in an upward direction. I will create my net force equation. So that fancy symbol right there is sigma, and for us in the physics world, that means the sum of. So the sum of all the forces is equal to negative 2 newtons. Where did we get that? Well, in the example problem, it says that after it's submerged in a liquid, it feels as if it weighs 2 newtons. So the weight is a downward force, okay? And it feels as if it weighs 2 newtons. So I wrote that as a negative 2. Remember, be careful. I never said that this object was floating. Okay? So that negative 2 newtons has to come from somewhere. And it comes from two forces, the force of gravity of the object, F of g, plus the buoyant force, or the upward liquid pushing force. All right? Now I'm going to fill in all of the values that I know. Right? We know that the box actually weighs 10 newtons, so I'm going to put in 10 newtons, but remember, weight always points down, so that'll be negative 10, and we're trying to figure out the buoyant force, so that'll be left alone. All right. Now, if we add 10 newtons to both sides, what we get is 8 newtons. So the liquid, or the water, is pushing upwards with 8 newtons of force. Now, because it's only pushing up with 8 newtons of force, the object feels as if it's 2 newtons. All right. Now, let's try another one. Let's prove Archimedes' principle with our equations. So we have a floating object. Now, if we have a floating object, there's a couple of things that we need to take into consideration. Before we do that, let's start off with our free body diagram. So we have an upward buoyant force. We have a downward force, which is the weight. And because it is floating, we can say that the acceleration is 0. Let's label the upward force the buoyant force, F of B, and the downward force as weight, F of G. Okay, I also wrote it in there as mg. You can also write it as W. It's your call. All right, writing out my net force equation, we know that the buoyant force is equal to the mass of the block times G, or so that portion is the weight. All right, now we're trying to prove Archimedes' principle, and Archimedes stated that the weight of the object is equal to the weight of the displaced fluid. Right? So I went ahead and I put that in there. Now, if you know a couple of things or two, we see two variables that look extremely familiar. So what we can do is actually knock it out. All right? Now, if we do that, what we get is Archimedes' principle. We can say that the mass of the block is equal to the mass of the displaced fluid. All right? Okay. Now let's try another example. We have a block and it's completely submerged and it's floating in a fluid. The block is suspended by a scale. If the block is 5 kilograms, but it has an apparent mass, okay, this is how it feels to the scale, all right, of 3 kilograms. What would the buoyant force be? What would the displaced volume be? All right, so for this problem, we have two questions that we are working off of. Let's solve both. So first things first, let's work off of this sketch. Let's add in all of the information that we know. We know there's an upward force, and we're going to call that upward force the tension, aka the force that the scale is exerting on the block to hold it up. Okay, and that is what the scale is reading. We also have another upward force, that is the buoyant force up. Okay, and that is from the fluid, or the liquid in which the object is submerged in. We also have the downward force, the weight, or F of G. Okay, so we're going to start off with our net force equation. We can say positive T plus positive F of B is equal to mg. Now you might be thinking to yourself, how did I get that? Why, like, I thought weight was going to be negative. But if you take a look at it, the net force equation normally would be positive T plus F of B plus negative mg is equal to 0, because it's completely suspended. All right, now because that's not the case that you see on the screen, what I did was I moved the F of G to the other side, making that negative a positive. So what that statement reads is all of the upward forces is equal to the weight. All right, now holy cow, where did this one come from? Let's look at it. So the tension is equal to the weight minus the buoyant force. So all I did was I subtracted the buoyant force from both sides. Now, if we do that, what we get is the apparent weight. And you see that right here as W subscript APP, or the apparent weight. That is what the scale thinks the fluid weighs. Okay? And the equation for weight is the mass times the force of gravity, or the acceleration due to gravity. And because it's not the actual or the real mass, we're going to write it as the apparent mass, as you can see on the screen. All right, so with that being, written down, let's think a little bit ahead. Let's use what we know. Let's try to create some different modes of thinking. So I'm going to write out our net force equation. We know that the net force is equal to the tension plus the buoyant force minus the actual weight, and all of that is equal to 0. It's 0 because it's suspended. Now, let's plug in some numbers that we know. So we know that the tension in the scale, or what the scale reads, is what the scale thinks it's reading, so the apparent weight. And weight is going to be mass times the acceleration due to gravity. Now, in order to make the math simple, I just used 10. Now, we have 3 times 10. That 3 came from the problem itself. So 3 times 10 plus the buoyant force minus the actual weight, 5 times 10, should all equal to 0. If this were the case, we will know that the buoyant force would equal 20 newtons. Now, let's see what that leads us to. Okay, If it were 20 newtons, there's a couple of things that should mathematically work out. Okay, so we know that the mass of the block is actually 5 kilograms, according to the problem, right? But the scale reads it as 3 kilograms. So what the fluid is doing is it's pushing up with about 2 kilograms worth of force, or 20 newtons of force. And if you do the math, we get 2 kilograms. So what the water is doing is pushing it up to take away about 2 kilograms worth of mass. So the scale only reads 3 kilograms. And that is the mass of the displaced fluid, according to Archimedes' principle. Now, if you're wondering, well, what can we do with this information? Well, with that information, you can find the displaced volume. We know that the buoyant mass is 2 kilograms. And we know that the density of the fluid, or at least for water, and I'm going to use water here, should be 1,000 kilograms per meters cubed. So if the buoyant mass is 2 kilograms, and we divide both sides by 1,000, we find out that the volume of the object is 0.002 meters cubed. Now, this is how you solve different kinds of buoyancy problems. The key things are to draw a sketch, do a free body diagram, and create a net force equation, and just go with from there. Good luck.